Welcome to the series How to Geometry, where I go through the basic geometry concepts in every video. I try to keep them in under 30 minutes. There's topics and then there's examples, and hopefully you get a lot out of these videos. Hopefully you learn something. If you haven't already, go ahead and subscribe, like, comment, hit the notifications bell so you never miss a video, and I'll catch you in the next video. Okay, so let's start by reviewing how to simplify radicals. I think that's a good place to start. All right, so simplifying radical expressions. The radical symbol refers to the positive square root of a number. The number variable under the radical sign is called the radicand, also known as the argument. Sometimes it'll be referred to as the argument, but for the most part, radicand. The number variable in front of the radical sign is called the coefficient. All right, simplifying radicals. Okay, so when you're simplifying radical expressions, the radical symbol is referred to as the positive square root of a number. And the number variable that's under the radical sign is referred to as the radicand. The number variable in front outside of the radical is called the coefficient. So you know when an expression with radicals is in its simplest form because the radicand will have no perfect square factors. There are no radicals in the denominator, happens to be a fraction, and the radicand itself, the part inside of the square root, does not contain any fractions or decimals. Those are the three things: no perfect squares, no radicals in the denominator, and no fractions inside of the radical. All right, so memorizing the list of perfect squares does come in handy. If the radicand is not a perfect square, right, you want to rewrite the radicand as a product of its largest perfect square factor. Then remove the perfect square factor from under the radical. All right, so let's see some examples. Let's look at root 8. If I want to simplify root 8, we're going to break this down into its prime factors. So 2 times 2 times 2. All right, we can pull out a pair as a single 2. And then whatever's left behind will be left in the radical. So the square root of 8 simplifies to 2 root 2. Square root of 80, so 2 times 40, 2 times 20, 2 times 10, 2 times 5. Here we can circle one pair, two pair of 2s. So each of these pairs are going to be pulled out of the radical as a single 2. So 1, 2, and then the square root will contain the leftover number, which would be 5. So in this case, the square root of 80 is going to be 2 times 2, which is 4, and then root 5. All right, root 27. 27 can be broken down into 3 times 9, and then 3 times 3. So we have a pair of 3s. That's going to come out as a single 3, and then square root of 3 left over. So 3 root 3. Hopefully you can kind of see where this is going. Still a couple more. So 120. The 120 can be broken down into, so if you don't want to start with 2 or 3, so typically it'll be 2, 3, 5, 7, and sometimes 11 and 13. But for the most part, you can break these down however you feel. I like using 2 or 3 just because it keeps the numbers organized. But if not, you can do something like this. There's 10 and 12, right? Because 10 times 12 is 120. 2 and 5. This will be 3 and 4. And then 4 is 2 and 2. I think this way gets kind of confusing because numbers are all over the place, but it still works. So here we have just a pair of 2s, and that's going to come out as a single 2. And left behind is going to be 2 times 5 times 3, which is basically root 30. So 2 root 30. All right, 180, this can be written as 10 and 18. 10 is going to be 2 and 5. 18 is going to be 2 and 9. And 9 is 3 times 3. Okay, here we have a pair of 2s. Here's a 2, there's a 2. That's going to come out as a single 2. And then a pair of 3s. That's going to come out as a single 3. And what's left behind? Root 5. So 180 is going to be 6 root 5. Last example, 90. So we can call this 9 and 10, right? 9 times 10 is 90. 9 is 3 times 3. 10 is 2 times 5. See that a pair of 3's will come out as a single 3, and then root. That is simplifying radicals. All right, next, adding and subtracting radicals. All right, you can only add subtract radicals if they have the same radicand. If the part inside of the radical matches, then you can add or subtract them only. So to add and subtract them, you want to simplify each term first, if possible, and then add the coefficients of the terms with the same radicand. So the inside parts are going to stay the same. All right, so think of it as if you were adding x plus x. All right, if you add x plus x, this would be 2x. So treat the square root as you would x. All right, if I'm adding root 2 plus root 2, I don't do anything with the root 2's, just like I didn't really do anything with the x's. It stayed the same. It's just a label. So this would really be 2 root 2, but you'll see that here in a second. I'm not going to work through all of these. I'll just do a couple. So let's see. So first we have 2 root 3 plus 5 root 3. This is going to come out 7 root 3. 3 root 2 minus 8 root 2. This will be, so we're subtracting a bigger number from a smaller number, so negative 6 root 2. So 3 root 2 minus 8 root 2. We're subtracting a bigger number from a smaller number. So this is going to be negative 5 root 2. Okay, next example, a little lengthy. So 4 root 5 minus 4 root 3 plus 9 root 3 minus 2 root 3. All right, we only have one root 5 term, so that guy is going to stay by itself. We can combine these three, however, because they all have matching radicands. So this is going to be minus 4 minus 2, so it's minus 6. Minus 6 plus 9 will be 3. So these will combine to make 3 root 3. And then 4 root 5 will stay in front. So this will be the difference, or the simplification of these four, basically. You can only combine 3 of them. Root 48, this can be broken down into 2 and 24, 2 and 12, 2 and 6, 2 and 3. So we have 2 pairs of 2's. So I can pull out a 4. 2 times 2 is 4. 4 root 3 plus 2 root 3 will be 6 root 3 plus 8. This is, let's do one more. 54. This can be 9 and 6. 9 is 3 and 3. 6 is 3 and 2. So a single 3 can come out. Root 6 is left behind. So 2 root 6 plus 3 root 6 will be 5 root 6. Here's kind of fun. Let's do one more. All right, so 12 can be broken down to 3 and 4. And 4 is 2 and 2. I can pull out a single 2. So negative 2 root 3 plus 3 root 3. This is going to be 1 root 3. So it's implied that there's a 1. So you don't need to write the 1. 27, that's 3 times 3 times 3. So 3 root 3. So 3 root 3 minus 3 root 3 is going to be 0. Okay, so that's adding and subtracting radicals. All right, multiplying radicals. Multiplying is a little bit less restrictive. The radicands don't have to match. All you do is multiply the coefficients, and then you multiply the parts inside the radical, and then simplify if necessary. So kind of like if you were multiplying 2x times 2x, right? 2 times 2 would be 4, and then x times x would be x squared. So you multiply the coefficients, then you multiply the radicals, the part inside the radicals, and then you simplify. So let's see some examples. So 8 times 8, 64. Square root of 64. That's going to be 8. This is actually a very interesting property. So whenever you're multiplying square roots and the radicals are the same, just as they are here. When you're multiplying two radicals with the same radicand, product, the answer, is just the part inside the square root. It is the radicand. So here we have root 8 times root 8. The answer is 8. That's the case for any two radicals that match. 2 times 6 would be 12. So root 12. This can be simplified. We can do 3 and 4. 4 is going to be 2 and 2. So this is going to be 2 root 3. Could we have simplified first? Yes, but I think it gets a little messy when you start simplifying first. Just do the multiplication first and then simplify last. So here we have 2 root 3 times root 3. So again, these two can multiply to make 3, and 3 times 2 would be 6. 2 times 5 is 10, and then 3 times 4 is 12. But we know that root 12 simplifies to 2 root 3 from a few examples ago. So it's going to be 10. This is going to be 2 root 3. 10 times 2 is 20 root 3. So simplify and then combine coefficients or multiply coefficients. All right, they get a little bit more interesting. So here we have, so coefficient times coefficient would be 5. It's 5 times 1, right? It's implied there's a 1 there. Inside the square root, 3 times 4 is 12. X times x is x squared, and then y. Okay, another interesting property is that when you have multiple things being multiplied inside of a square root, we can split the square root up. What am I saying? I'm saying the square root of 12, the square root of x squared, square root of y. All right, 12, we've already seen, that's going to be 2 root 3. When you square a square root, they cancel each other out. So x squared, the square root of x squared is just x. And then the square root of y is the square root of y. Don't forget about the 5. So final answer is going to be 10x root 3y. We can put it back together. Okay, this one looks fun. So coefficients first. It's going to be 10x square root. We're going to multiply everything inside the square root. This is going to be 18. When you multiply common bases, we add the exponents. So x to the 6th, y to the 6th. Okay, simplifying this, 18 is going to be 2 and 9, 3 and 3. So 3 is going to come out. So it's going to be 30x. Left behind is going to be a 2. Okay, x to the 6th. So think about what this means. This is saying x times x 6 times. So I can pull out every pair. So I can actually put out 3 x's. So that would be x cubed. X cubed is going to come out, but there's already an x outside. So this is going to be x to the 4th. Y to the 6th. Again, same logic. There is 6 y's, so I can pull out 3 y's. So this is going to be y cubed. I'll see one more example. This one's, we have to kind of do like a FOIL kind of method here. Since there are two binomials being multiplied. So if we use first, so this is going to be 15 outer, 5 root 3, inner, 12 root 3, last, it's going to be 4, and root 3 times root 3 is 9. No, I take that back. Root 3 times root 3 is 3. 3 times 4 is 12. So combining like terms, we're going to get 27 plus 17 root 3. So double distribution has to happen right there. Otherwise, AKA FOIL. Okay, when we raise a power to a power, you're going to raise, when we raise a radical to a power, we're going to apply the power to the coefficient, and then you apply the power to the radicand, the part inside the square root. So you're going to apply the power to both the coefficient and the radical separately, then simplify. So let's see a couple of examples. Square root of AB squared. When you square a square root, it actually cancels each other out. So it's just going to be a, that's actually kind of nice. Root 2 squared, again, square root and the square cancel each other out, and the answer is 2. Okay, here we go. This one's a little bit better. So root 2 cubed. So a couple ways of thinking about this. This means root 2 times root 2 times root 2, right? 3 times. So root 2 times root 2, this is just 2, times root 2, nothing can be done. So 2 root 2, that's the answer. It is worth mentioning right here that when you have a square root with the power, you could actually apply the power to the radicand, the part inside the square root. So this would be 2 cubed. So 2 times 2 is 4, times 2 is 8. So the square root of 8. Now when you simplify this, you get 2 times 4, 2 times 2. You can pull out a pair of 2's. So 2 root 2. Again, we see that that's the same solution. So here a good property is it comes in handy sometimes to know that the power can be either outside of the parentheses or applied to the radicand, the part inside the square root. Okay, 2 root 5 all squared. So we're going to apply the power, the coefficient, and then to the part inside the square root. So 2 times 2 is 4, and then 5 squared is 25. Square root of 25 is just 5. So 4 times 5 would be 20. Here we see that the square root and the square cancel each other out, and we're left with 2 root 3. Okay, they do get a little bit bigger. So here, putting the exponent on the radicand probably wouldn't be that efficient. So if we did root 4 times root 4, that's going to be 4 for sure. But it's 4 times, so root 4 times root 4 again. Again, that's 4. When you multiply those together, we get 16. Okay, this one looks a little tricky because there's a cube. So this cube does not apply to the 3 in front, right? It only applies to what's inside the parentheses. So it's going to be 3. Then we could do root 5 times root 5 times root 5. This is going to be 5 root 5. So 3 times root 5 times 5 would all be 15 root 5. Let's do one more. So this is going to be 5 cubed root 3 cubed times 2 squared times, it's going to cancel, so it would be times 2. All right, so doing all the coefficients first. So 5 times 5 times 5, 125 times 4, right, because 2 squared times 2 times root 3 cubed. 4 times 2 is 8. Or actually, let's do it like this. 125 times 4 would be 500. 500 times 2 is 1,000. And then times root 3 cubed. That's going to be 3 root 3, which is 3,000. I know it's going kind of quick, but you can always pause it and do the calculations for yourself. Okay, dividing radicals. I believe this is the last topic. So when you're dividing radicals, the idea is that we don't want radicals in the denominator, and we don't want radicals, or we don't want the radicand to have any fractions or decimals. So no radicals in the bottom of the fraction, and no fractions inside of the square root. All right, so let's see. Do a couple. So the idea here, there's another property, a square root property, that I can take the square root of the top and the square root of the bottom of a fraction. So this is going to be the square root of 4 over the square root of 25, which 2 over 5. So square root of the top, square root of the bottom, we can split them up. So we did the same thing here. Square root of the top, square root of the bottom. Square root of the bottom is easy. It's going to be 5. Hopefully you can see that. Square root of the top. So 4 times 2, and then 2 times 2. So 2 root 2 over 5. That's the answer here. Okay. Check it out. We want no square roots in the bottom. So root 3 over root 2. So here, the bottom isn't a clean, perfect square like the other two examples. So what we want to do here is multiply fraction by root 2 over root 2, right? Because anything divided by itself is 1. And when you multiply anything by 1, you don't change the value, right? Anything times 1 is itself. Well, here we're multiplying by a clever one. So this is going to be, the denominator will be 2 under root 6, right? 3 times 2 is 6. So root 6 over 2. So again, no square roots in the bottom. Do a couple more. A few more, actually. Okay, so can't be simplified anymore. Root 3 over root 3. So immediately, when you can't simplify it, whatever that denominator is, that's what you're going to multiply the whole fraction by, top and bottom. And the bottom by design would just be 3 over root 15. All right, root 3 is in the bottom. Immediately, I know that that's what I'm going to multiply top and bottom by. This is going to be 3 over 4 root 3. Not bad. Root 3 over root 3 is going to be 3, 15, root 3. Here, we can simplify further, right? 3 goes into 3 once, 3 goes into 15 5 times. So 5 root 3. Do a few more. Root 2 over root 2. So 2, 6 root 2. This can simplify to 3. 3 root 2. 2 more, and then we'll call it a night. So this is going to be root 2 over root 2. 2. Feel like we did that one already. Root 6 over 2. Okay. All right. For this guy here, 2 root 5 over 3 root 3. We don't want square roots in the bottom. So we could multiply this by 3 root 3 because that's what's in the denominator. But if we multiply by just root 3, this will work also. Because once these two crash, it'll just be 3. And then times 3 because of the coefficient. So this is going to be 3 times 3, right? Because when root 3 times root 3 is 3, this 3 is from the coefficient. So that's basically 9. And then up top, we have 2 root 15. So final answer, 2 root 15 over 9. That doesn't simplify anymore. All right, so hopefully this was useful, and you can always go back and review this. If you haven't done so already, be sure to hit the subscribe button, the notifications so you never miss a video, and comment, like, tell me what you think, and I'll catch you in the next video.